In the previous video, we started looking at the k-means algorithm for clustering. And we started with this intuition that we wanted to assign points to a cluster, that to a center, that each cluster has a center and the points in that cluster are nearer to that center, but you have to choose the centers. And so we wrote down this sort of objective function that we wanted to minimize. And then we said, okay, so in k-means, we're going to alternately choose the optimal A for a fixed mu, the optimal assignments for fixed centers, and then for fixed assignments, we'll choose the optimal centers, starting from some initialized, say, randomly chosen centers. And in step A, we found that the optimal assignments are just the nearest. Choose the center that's the nearest to that point. And now we need to choose the optimal centers for given assignments. So we want to minimize optimal in the sense that it minimizes this objective function. So let's write down this objective function and let's try to minimize it for fixed A. Let's minimize it with respect to mu, each of the mu's. So let's write this down here. Let's rewrite it first. L is the sum. The sum as I goes from, I guess I did j first. J from 1 to k, I from 1 to n, aij, distance from xi to mu j squared. And this squared Euclidean distance we can also write as, well, let's actually so let me just say that first, I guess. This squared Euclidean distance is the dot product of xi minus mu j with xi minus mu j, of course. And now we want to, so we do the standard calculus thing, set the gradient of L, and this is the gradient with respect to mu j for pick one j, and we're gonna try to minimize L with respect to one of these mu's. So in fact, this sort of decouples into the sum of these j things, and they're sort of they're independent because each of the terms in this sum only depends on mu j. So it decouples, and let's minimize it with respect to one of these. So let's take the gradient. So we have the sum. We may as well just put sum over I and j. Well, no, let's keep them separate. Sum over I, sum over j. Aij, I'm moving the gradient inside the gradient of this thing, xi minus mu j. Oh, and actually, so right, we can first, if we're taking the gradient, I should have made this like j prime or something here. J prime, xi minus mu j prime. But the gradient of mu j prime whenever j prime is not equal to j is just 0, and xi doesn't depend on mu j. So this is just 0 unless j prime equals j. So we may as well just leave these as j, and we can get rid of this sum, xi minus mu j. So we're just left with the one term here. And let's take a closer look at this expression here. So let's expand it out. We have the gradient of xi transpose xi minus mu j minus 2 times mu j transpose xi plus xi, or plus rather mu j transpose mu j. And if we move the gradient through, this part doesn't depend on mu j at all, so this is 0. This, using just a little bit of vector calculus stuff, this is minus 2xi. You can write out what the definition of the gradient and verify that if you want. And this is 2 mu j. You can check those if you wish, if you aren't familiar with those little rules for vector calculus. And so we can plug that in above here. And what do we get? Well, so let's say, I'll just put it down here. Should I put it down here? I'll just put it up here, I guess. So if we plug those in, we get the sum over I, aij minus 2xi plus 2 mu j. And now continuing this line down here, so that was an aside. Now this equals, what is it? Minus 2 sum of aij over I plus 2. Now this doesn't depend on I, so we just get, oh sorry, there should be an xi in there. aij xi plus 2. This doesn't depend on I, so now we get mu j sum of the aij's over I. And let's give this, well, okay, so we'll come back to that in a sec. So now, so we set this equal to 0. And we want to solve, so that gives us, the 2's cancel, move this one over, divide by this, and we get mu j equals sum over I aij xi divided by sum over I aij. And let's check that this is, so this is a critical point, it's a unique critical point, and let's just check that it's a, well, let's see, we want it to be a minimum, so let's just check that it's a minimum. So if we took the second derivative, if we took a derivative with respect to, you know, say mu, I don't know, mu jk, the kth component of j, then what do we get? So the second, so it's the derivative of the gradient. So we want to get the Hessian. In order to verify that this is in fact a minimum, we want to get the Hessian. So we have to take the matrix of second derivatives. And so we differentiate this, and what do we get? Well, this is 0. So the derivative, you know, moves through here. This is 0. And this is just equal to, this is a constant, so we get 2 times that constant. Times, if k equals, so it's going to be 0 for the component. So this is a vector. We're differentiating this vector, and it's going to be 0 for the elements where it's not equal to k, the elements that are not k, and it's going to be 1 for the elements that are k. So this is going to be ek. This is the, you know, if E1 is 1, 0, the standard basis. E2 is 0, 1, 0, 0, etc. And so the matrix of second derivatives, the Hessian, is this thing 2 times the sum of these guys times the identity matrix. And as long as one of these, as long as there is at least, so as long as this is non-zero, then this is positive definite. And therefore it's a minimum. So is it always true that at least one of these is, so these aij's are always 0 or 1, so we need at least one of them to be a 1. And what does that mean? What is this aij? Well, so let's think about what this aij means. Sum of the aij's. What's aij? There it is. aij is 1 if xi is assigned to j. So if we're summing over I, summing aij over I, then that gives us the number of points that are assigned to j. So let's write that down. So let's call it nj. nj, sum as I goes from 1 to n, aij, equals the number of points I such that xi, a number of I such that xi is assigned to the center j. So this is going to be positive definite as long as there's at least one point assigned to that center. So let's assume that there is for now. Let's assume, so this is assuming nj strictly positive. So by the way, this notation for a matrix, the positive, greater than 0 notation means that something's positive definite. And you put greater or equal to mean it's positive semi-definite for a matrix. And now, so what is this formula saying? So now we have this formula here is saying to minimize L for mu j, the mu j, the choice of mu j that you should choose is this 1 over nj times this sum. And what is this sum? This is the sum over all the elements. This is the sum over all the points xi, such that xi is assigned to j. So let's just write out that sum over all I, such that xi is assigned to j of xi. And this formula here has a very natural interpretation. So this is going to be our formula. This is going to be our update for the B step in the algorithm. So we'll choose the new mu j for each j to be just the empirical mean. This is just the empirical mean of the points that are assigned to j. And so technically speaking, this is not defined when nj is 0, but that happens so rarely. In fact, whenever I've used k-means, that's never happened to me. It happens so rarely that I don't know if there's a standard approach to resolving that, but one thing you could do would be to just restart the algorithm from the beginning with a new random initialization. Or another thing you could do, which would, if nj was 0, another thing you could do would be to just, so that would mean that there was, some center j for which no points were assigned to it. So another thing you could do would just be to randomly set that mean to one of the points in the data set. And then that point would be guaranteed to at least be assigned to that on the next go around. So that's a couple of ways. So this is the k-means algorithm. So you start out, so you're iterating between A and B, and in step A, you're choosing these assignments. Assign each point to the nearest mean. And in step B, you're updating each mean to just be updating each center to be the empirical mean of the points assigned to it. So that's k-means. And k-means, it's not guaranteed to converge to the global minimum of this function. In fact, I think that this finding the global minimum is actually an NP-hard problem. And so this simple iterative scheme is not guaranteed to give you the global minimum, but oftentimes it works quite well, and it's usually pretty fast. So that makes k-means a fairly popular method. And next, or a little in the near future, we're going to look at an alternative to k-means, a more sort of probabilistic approach to clustering using a Gaussian mixture model, and we'll use EM, the expectation maximization algorithm, to find a good choice of Gaussian mixture model for clustering the data.